This schematic represents a major architectural fracture in modern software. The single deterministic pipeline, where data flows predictably from input to output, shatters into a highly complex, multi-agent orchestration web. Enterprise AI workloads have outgrown single prompt executions. When tasks require varied domain expertise, like querying a database, synthesizing internal documents, and drafting code, teams deploy specialized agents to collaborate and solve problems iteratively. This shift replaces linear code with autonomous agents, introducing severe, compounding stochastic risk. You are handing logic control over to a probabilistic engine. These agents operate on a perceive, reason, act, learn cycle. An unhandled hallucination or logic error in an early reasoning step stops the local process and irreversibly corrupts the context window for every downstream action that follows. Safely scaling AI into production requires engineering rigid, state-driven boundaries to contain this non-deterministic behavior. This maps the NIST 4 tiers of AI autonomy, from Level 1, fully supervised, up to Level 4, fully autonomous. At Level 4, without real-time oversight, emergent risks materialize. Combining multiple agents produces unpredictable behaviors no single assessment can identify. Securing Level 4 autonomy requires 3 specific architectural guardrails: strict JSON-schema tool governance, distributed circuit breakers, and engineered human-in-the-loop pause states. Implementing these 3 guardrails provides the mandatory operational foundation for enterprise production. Autonomous agents fail when deployed inside linear directed acyclic graphs, or DAGs. Because a DAG forces a strict one-way execution path, an agent cannot retain memory across steps or self-correct if it makes a mistake. This side-by-side comparison shows the structural solution. On the left is the rigid DAG pipeline. On the right is a cyclic workflow built in frameworks like LangGraph. Cyclic workflows allow agents to evaluate intermediate results, revisit previous steps, and adapt their approach dynamically. Notice the orchestrator node on the right. It acts as the central decision maker. If an output fails an internal quality check, the orchestrator routes the task back to a planner node to try again. All of this is powered by a persistent state object. Under the state graph mechanism, every agent reads from and appends to a centralized shared state ledger, rather than passing isolated variables blindly down a chain. Treating the AI workflow as a persistent state machine gives engineers the ability to pause, inspect, and resume execution at any microstep. Multi-agent systems are cyclical state machines, requiring entirely new control layers that traditional CI/CD paradigms don't provide. Emergent behavior occurs when an autonomous agent is given unstructured access to combine tools, such as pulling a secure database query and immediately formatting it into an external web request. The first architectural rule is isolation. An LLM must never directly execute an open-ended function against external infrastructure. Instead, the architecture requires a quarantine layer. This diagram shows an incoming LLM output hitting a gatekeeper that validates all stochastic tool calls against strict, predefined JSON schemas. If the proposed parameters fail exact schema validation, like attempting to send data to an unauthorized URL, the execution is forcefully blocked and logged for review. Schema validation functions as the primary blast radius reduction tool, isolating core infrastructure from hallucinated API parameters and prompt injection attacks. Without proper controls, autonomous agents enter infinite maker-checker loops, constantly debating themselves, or hang indefinitely when interacting with degraded external APIs. Relying on naive timeout configurations is insufficient. This architecture introduces the circuit breaker pattern, a method for monitoring and containing downstream failures. When a failure threshold is crossed, the circuit trips into the open state. It immediately rejects requests and fails fast, preventing the system from exhausting compute resources or burning through token limits. After a timeout, the circuit enters the half-open recovery state. It allows a limited number of requests through to test if the downstream dependency has stabilized before closing the circuit again. We apply this same logic at the application level. By enforcing hard iteration caps, like a max replans constant, the orchestrator forces an end to endless reasoning cycles. Circuit breakers transform catastrophic system-wide hanging into predictable, graceful degradation. Allowing agents to execute high-risk, privileged operations without human oversight violates enterprise compliance frameworks like ISO 42001 and the EU AI Act. Cyclic state machines solve this by supporting pause states. When the graph reaches a node designated for high-risk execution, the workflow halts. At this checkpoint, the system serializes the complete state ledger and persists it to a database. The agent is taken offline. An external human operator can then review the persisted context. If they inject an approval signal, the system rehydrates the state, and the workflow resumes from that exact node, without needing to rerun previous steps. This asynchronous authorization layer enables the human oversight required for Level 3 and Level 4 autonomy. The architectural paradox of AI is that autonomous agents require cyclical freedom to reason, but that freedom creates unacceptable risk in production. This architecture resolves the paradox. By layering schema validation, circuit breakers, and human-in-the-loop pause states, engineers create a deterministic containment shell around a non-deterministic agent core. Implementing these specific technical boundaries is how engineering teams translate abstract governance frameworks into executable code. Model scaling provides more reasoning depth, but it cannot solve the structural risk of stochastic failure. Achieving production-grade reliability depends on the resilient, governed system architecture engineered around that model core.